Here we are at the last part of Lecture 9. This should be Lecture 9c. We're looking at the temperature dependence of the Gibbs free energy. That's what we want. Let's just go to the cut to the chase here. This is what we get. It's called the Gibbs-Helmholtz relation. This, you probably don't recognize it in its present form, but as you'll see as we develop this equation, that this in fact is what you learned in introductory chemistry. That a plot of log K versus 1 over T gives you the standard enthalpy of formation, perhaps in a little different form. All right, so let's go ahead and try to figure out what the temperature dependence of the Gibbs free energy will be. In other words, what we want is how G changes with temperature at constant pressure and number of moles. Remember that G, we said now, is a function of three variables: temperature, pressure, number of moles. Let's hold these constant while we just look at the temperature dependence of T. Now, what do we really want? We want to relate equilibrium constant to temperature, really, because that's something we can measure in the laboratory. Remember that delta G is a delta G0 plus RT times the natural log of Q. Or at equilibrium, delta G0 is minus RT times the natural log of the equilibrium constant K. This is at equilibrium. And so it's log K, the temperature dependence of that. Let's put this temperature over here, so we're actually looking at delta G0 over T. That will be equal to R ln K. I hope I convinced you by this little argument that really we should be looking at, because this is where we want to go related to equilibrium constant, that we should be really looking at the temperature dependence of G over temperature. So let's look at how G over temperature varies with temperature at constant pressure and number of moles. All right, so G will depend on temperature, and certainly temperature depends on temperature. So we have to use that rule of calculus, which I can't really remember, but it'd be the first, G times the derivative of the second, 1 over T, how that varies with T, plus 1 over T, how G varies with temperature at constant pressure and number of moles. This also is constant temperature and number of moles. All right, so this would be G. We can take the derivative of 1 over temperature with respect to temperature. We got minus temperature squared plus 1 over T. Oh, remember what this is? How G varies with temperature, constant pressure, and N? That is equal to minus S from, I think, Lecture 8, last lecture. That's kind of cool. So we can just put a minus S here. Okay, now let's multiply this by, so we want to collect terms here, so we want a T squared there, so multiply this by T over T. That's 1, we can always do that, so we'll get the T squared there. This will be TS. So by doing those manipulations, we end up with minus G over T squared minus TS over T squared, and that's just equal to minus G plus TS over T squared. And remember that G was defined as H minus TS, so that G plus TS is equal to H. All right, let's just put H in there. This is minus H over T squared. So this says that how free energy changes, how free energy divided by temperature changes with temperature is related to the enthalpy of the whatever we're looking at. This is called the Gibbs-Helmholtz relation. And again, what we're looking at is how G over T changes with temperature at constant pressure and number of moles. All right. Now, let's relate the Gibbs-Helmholtz relation here. Let's relate that to equilibrium constant. So we had, let's see, delta G0 is RT times the natural log of K, or delta G0 over T is related to the natural log, sorry, I forgot about that R times the natural log of K. So let's take the derivative of both sides with respect to temperature. So the derivative of G0 over T, well, we can actually put a delta here, because when you do G, you just put a delta there and a delta there. Actually, let me be explicit about that, just rather than throwing it out there. So keep those in mind. In just a second we'll use those. Okay, so I also claim that this can be written as how delta G over T changes with temperature at constant pressure number of moles. That's equal to minus delta H over T squared. All right, so we just replace the G by delta. You can see that by the delta means final minus initial. So you just write, final minus initial, and you get the same thing. Okay, so let's go to the next page here and put in, instead of delta G0, which will mean this delta H will be delta H0. So how delta G0 over T varies with temperature, that's equal to minus delta H0 over, what do we say, T squared. All right, we know that delta G0 is minus delta G0 over T. We just said that. I'll just rewrite it here. Delta G0 over T is equal to R minus, there's a minus sign there. Getting too excited here. I should calm down. All right. Got to figure out the shortcut for felt tip pen. So minus R times the natural log of the equilibrium constant K. So this is also equal to how the minus R times ln K changes with temperature. So let's rewrite this. We have how let's just do the ln of K versus temperature, and we're going to put the minus R over there. That's equal to delta H0 over RT squared. Well, we can do a little simplification here. Know that we can actually show this. A derivative of, or d1 over t, is equal to minus derivative of t over t squared. So you take the derivative with respect to 1 over t, that's minus 1 over t squared. Or in other words, that the derivative dt is equal to minus t squared times d1 over t. So that's what we're going to put in there. So we have how natural log of k changes 1 over temperature, and here we have minus 1 over t squared. That is equal to delta H0 over RT squared. Let's multiply by minus t squared. That will go away. So what we end up with is the derivative, or how ln K varies with 1 over temperature. That's just equal to minus delta H0 over R. In other words, if you measure the equilibrium constant as a function of 1 over temperature, so this would be K, and let's plot the natural log of the equilibrium constant versus 1 over temperature. We're going to get some data that either be positive or negative, but what we're saying here is the slope will be equal to minus delta H 0 over r. Or in other words, delta H0 will be minus r times the slope of this line. So there's a way to get a standard enthalpy change for some reaction. Just measure the equilibrium constant for the reaction as a function of temperature and plot log equilibrium constant versus 1 over temperature. The slope will give you, and multiply it by minus r. That will give you the standard enthalpy change. Alright, so notice that this is the slope at any particular temperature. Let's integrate both sides of this. So we'll multiply by 1 over t. So let's integrate ln k going from k1 to k2, initial and final state. That's equal to minus, or the integral going from t1, corresponding to that equilibrium constant, to t2, of minus delta H0 over r integrated over d 1 over t. This is d log k. Let me just try to clean that up a little bit here. Alright, so d natural log of k. Alright, so let's go ahead and integrate that. On the left-hand side, we got the natural log of k2 final over k1 initial. That's integral to delta H0 over r d 1 over t. Now what we're going to do is, well, r is a constant, so we can pull that out. But let's assume that delta H0, the standard enthalpy of the reaction, does not depend on temperature. So we can pull that out. So delta H0 over r, the integral of 1 over t, evaluated between t1 and t2. Here we're assuming that delta H0 is independent of temperature. And that then is equal to just delta H0. And of course I forgot the minus sign there. Okay, so did I get the minus sign here? There it is there. So I forgot to carry it along. Minus delta H over r 1 over T2 minus 1 over T1. This you may or may not recognize is the equation that's thrown out in introductory chemistry. Just write what's over here, ln of K2 over K1. So you have 1, 2, 3, 4, 5 things, and if you know any 4 of the 5 things, you can calculate the 5th. So for example, if you know the standard enthalpy of reaction, and you know the equilibrium at one equilibrium constant at one temperature, then you could find the equilibrium constant at another temperature. So again, this is an example. You learn chemistry at various stages. So in introductory chemistry, we knew about this, and now we were able to derive this using the fact that, or using our partial differential skills, and this cool thing here that where is it? It's around here somewhere. There it is. That how G changes to T at constant pressure or moles is minus S. So that cool thing and the partial derivatives and all that other stuff, we end up with the equation that's thrown out in introductory chemistry. All right, so that ends lecture 9, and I'll now go work on lecture 10.